All right, we're going to look at a second truss problem. It's a different three-member truss. Again, step one is figuring out the angle of rotation for each member from the same coordinate system. So member one, this is theta 1. Member 2 is horizontal, and that is theta 3, not the interior angle. Okay, so you have to rotate them all the same direction, either clockwise or counterclockwise, and typically we use counterclockwise. Once we know our angles, I'm going to determine my local stiffness matrix and global coordinates for each element using the code that I have derived. In this case, you get K1, K2, and K3. I will post a MATLAB video as well. So now we're going to look at our nodal continuity and force balance. So here's point 1. We know at point 1 we have end 1 of element 1 and end 1 of element 2. At point 2 we have end 2 of element 1 and end 1 of element 3. Because I labeled it this way. If you were to number your picture differently, you would get a different nodal continuity. And at point 3, we have N2 of element 2 and N3 of element 3. Same for our forces. These are not equal to 0. Those are our unknown reaction forces. Now, F2x is equal to 0 because it's unsupported and there's no applied load in the x direction. F2y is minus 20,000 pounds. I'm sorry, these should be plus signs. Now for element 3, because we have rollers here, there cannot be a force in the x direction, but there will be a reaction force in the y direction. So we're going to assemble our global stiffness matrix. We're going to do that by looking at our local relationship. Again, these are plus signs. And really we're going to be looking at what connects our 2 points. So what connects points 1 and points 2? Well, that's element 1. What connects points 2 and 3? Sorry, what connects points 1 and 3? That's element 2. And lastly, what connects points 2 and 3? Well, that's element 3. If you can figure out where the elements go, you can really easily number them. Since each node has 2 components, the elements in rows 1 and 2, 3 and 4, and 5 and 6 again are the same. We always start numbering with 1, 1 in the top left-hand corner of when we see our new element matrix. And we just add 1 as we go across. Again, we're asking ourselves what connects these 2 points from which end, remembering now that our element which still has 2 ends, has 4 designations where 1 and 2 are one side and 3 and 4 are the other side. The diagonal is always a duplicate subscript, and our matrix is symmetrical. If you get a non-symmetrical matrix, you have done something wrong. Go back and check. So again, we're going to apply our boundary conditions. These aren't 0. These are unknown. This one is 0. As is F3x. We know our displacements are 0 because they're fixed. U3 is not 0 because we have a roller in the x direction and it is allowed to move. All right, so we're going to remove the rows and columns with known displacements, basically allowing us to eliminate some of our unknowns. And we're going to keep our matrix square and look at our condensed system of equations. Please keep in mind, if a displacement was non-zero, you have to move it to the other side of the equation. We are just manipulating our set of equations by adding and removing some. At this point, we would use our favorite matrix solver to solve our system of equations, and we would get our unknown displacements. Once we know our unknown displacement, once we have solved for our unknown displacements, we're going to go back and solve for our unknown reaction forces. And it should be of no surprise that 12,000 and 8,000 add up to 20,000 because from a static standpoint, our reaction forces have to be equal to our applied forces.